For years, Pluto sat just barely out of reach of the James Webb Space Telescope's most detailed instruments, too faint, too small, and too close to its largest moon, Charon, for Webb to cleanly separate the two worlds' signals from each other. Then, in 2022, using a specialized infrared instrument, astronomers finally managed to do exactly that for the first time. Isolate Pluto's own faint thermal glow, completely distinct from Charon sitting right beside it. What they found, published across a series of papers through 2025, upended a basic assumption about how Pluto's climate actually works. For decades, scientists generally assumed that Pluto's thin, wispy atmosphere of nitrogen and methane gas was the primary thing controlling its temperature. The same basic mechanism that governs weather and climate on every planet with a substantial atmosphere, including our own. Webb's data revealed something genuinely counterintuitive instead. Pluto's climate isn't primarily controlled by its gas at all. It's controlled by haze, a thin layer of solid particles floating high above the surface, acting less like a blanket and more like an active thermostat, actively cooling the atmosphere to temperatures roughly 30 degrees Fahrenheit, colder than standard gas-only climate models ever predicted. That's not a small technical footnote. It's a genuinely different kind of climate system than anything else known to exist anywhere in our solar system. And remarkably, it was specifically predicted years in advance by a scientist who had no way of testing that prediction until Webb's instruments finally became sensitive enough to check. This is the story of how James Webb finally got its first clear look at Pluto, what it actually found, and why a distant, tiny, frozen world at the edge of the solar system is now teaching planetary scientists something new about how atmospheres and haze can interact anywhere in the universe. A quick, honest note up front: this discovery doesn't involve anything actually impossible, despite how some framing around it gets pitched. What's genuinely remarkable here is more specific and honestly more interesting than that. A precise scientific prediction made years before the technology existed to test it that turned out to be exactly right. To understand why this discovery matters, you first need to go back to 2015, when NASA's New Horizons spacecraft became the only mission in history to fly directly past Pluto and to a specific, surprising detail buried within the data it sent home. New Horizons revealed Pluto to be a genuinely active, complex world, not the simple, inert ball of ice many scientists had expected, but a landscape featuring towering ice mountains, vast nitrogen ice plains, including the now famous heart-shaped region called Tomball Regio, and clear evidence of ongoing geological activity. But one of the mission's biggest surprises floated well above all of that surface detail: a distinct bluish, multi-layered haze blanketing Pluto's sky, extending more than 185 miles, or roughly 300 kilometers, above the surface, far higher and far more intricately structured than any pre-flyby model had predicted. Before New Horizons, most scientists' expectations for Pluto's atmosphere were built almost entirely on theoretical modeling and indirect observations gathered from Earth, since no spacecraft had ever visited before. Those earlier models generally treated Pluto's atmosphere as a simple, relatively uniform layer of gas, without accounting for the possibility of a complex, multi-layered haze structure extending so far above the surface. When New Horizons cameras revealed dozens of distinct haze layers stacked on top of each other, visible in stunning detail as the spacecraft looked back at Pluto silhouetted against the sun during its 2015 flyby, it immediately became clear that Pluto's atmosphere was considerably more intricate than anyone had previously modeled, setting up exactly the kind of open scientific puzzle that Zhang's 2017 prediction was specifically designed to help address. That haze immediately raised an interesting theoretical question. In 2017, planetary scientist Shi Zhang at the University of California, Santa Cruz, led a team that made a specific, testable prediction based on this newly discovered haze layer. If the haze behaved the way their models suggested, it should make Pluto unusually bright, specifically in mid-infrared wavelengths of light, a very particular kind of signature that, at the time, simply couldn't be tested using any instrument then available to astronomers. It was, in essence, a prediction placed in a bottle, waiting for a telescope sensitive enough to eventually check whether it was right. That opportunity finally arrived in 2022, when the James Webb Space Telescope's mid-infrared instrument, known as MIRI, was used to observe the Pluto-Charon system directly. This wasn't a simple, casual observation, cleanly separating Pluto's own faint thermal signal from that of Charon. Its unusually large companion moon, orbiting extremely close by, represented a genuinely difficult technical achievement. The first time any instrument had managed to isolate the two worlds' individual signals this precisely at these specific wavelengths. Once the data came back, the result confirmed Zhang's 2017 prediction almost exactly. The faint infrared glow of Pluto's haze matched what his team had calculated years earlier before Webb even existed. As Zhang himself later put it, In planetary science, it's genuinely uncommon to see a specific hypothesis confirm this cleanly and this quickly within just a handful of years of first proposing it. Let's walk through exactly what that 2222 observation, once fully analyzed, ultimately revealed, because the details go considerably further than simply confirming a haze layer exists. The full analysis, led by Tanguy Bertrand, an astronomer at the Paris Observatory in France, was published in Nature Astronomy on June 2, 2025, with a closely related mid-infrared analysis separately published in the journal Astronomy and Astrophysics in April 2025. Using MIRI, the research team measured how the combined heat signal, or flux, from Pluto and Charon varied across several specific infrared wavelengths, 15, 18, 21, and 25 micrometers, as both worlds rotated. Those variations in emitted heat are directly sensitive to the specific properties of the surface material being observed, whether it's methane ice, water ice, or darker surface deposits, allowing researchers to compare Webb's actual measurements against detailed thermophysical models built to predict how different surface types should behave. The central headline finding to come out of that analysis: Pluto's climate and weather patterns are not primarily driven by its thin nitrogen-methane gas atmosphere, the way scientists had generally assumed for decades. Instead, they're driven by that high-altitude haze layer, which functions less like simple atmospheric insulation and more like an active planetary thermostat. During Pluto's day, haze particles absorb incoming sunlight. During its night, those same particles radiate that absorbed energy back out as infrared heat, escaping into space. Critically, that haze-driven cooling process works considerably more efficiently at regulating temperature than gas molecules alone ever could on their own, which is precisely why Pluto's upper atmosphere measures in at an extraordinarily frigid negative 333 degrees Fahrenheit, or negative 202 degrees Celsius, roughly 30 degrees Fahrenheit, colder than gas-only climate models, built without properly accounting for the haze's active role, had predicted it should be. That mechanism deserves a slightly closer look because the physics involved is genuinely elegant once you walk through it. Haze particles, being solid rather than gaseous, behave fundamentally differently when it comes to absorbing and releasing energy. A gas molecule generally needs to collide with other molecules to exchange heat efficiently, a relatively slow, diffuse process in an atmosphere as thin and sparse as Pluto's. A solid haze particle, by contrast, can directly absorb incoming sunlight and directly radiate that energy back out as infrared heat, without needing that same kind of molecular collision to move energy around. In an atmosphere as thin as Pluto's, where gas molecules are spread out extremely sparsely, that difference turns out to matter enormously, giving the haze a dramatically outsized influence over the atmosphere's overall temperature, compared to what the relatively sparse surrounding gas could achieve entirely on its own. That's a genuinely significant gap between prediction and reality. 30 degrees Fahrenheit is a substantial discrepancy in planetary climate modeling, large enough that any climate model built without properly accounting for this haze-driven cooling mechanism would have meaningfully misjudged one of Pluto's most basic physical properties. And Pluto isn't a minor obscure member of our solar system either. It remains one of the most extensively studied of the dwarf planets, thanks specifically to New Horizons' historic 2015 flyby, which means this specific discrepancy had real, practical consequences for how confidently scientists could model conditions on a world they'd already invested enormous effort in understanding. There's an additional, genuinely strange detail layered on top of the haze discovery. Webb's data also confirmed a bizarre interaction between Pluto and its large moon Charon, something unique within our entire solar system. Material actually escapes from Pluto's thin atmosphere and travels across space, eventually settling onto Charon's polar regions, a process researchers describe as depositing material from one world's atmosphere directly onto the surface of its neighboring moon. Webb's observations revealed clear differences between regions on Charon covered in pure water ice versus its darker polar regions, where this transferred material from Pluto appears to accumulate and evolve over time, offering new, more detailed insight into a phenomenon nothing else in the solar system currently replicates. Here's where it's worth explaining exactly why haze controls the climate, not the gas, is such a genuinely unusual finding, rather than simply an interesting technical detail. On essentially every other planet or moon in our solar system with a meaningful atmosphere, temperature, and climate are primarily governed by the behavior of atmospheric gas itself, how it absorbs and redistributes heat, how it circulates, how greenhouse gases trap or release energy. Earth's climate, Mars's climate, even Venus's famously extreme greenhouse climate are all fundamentally gas-driven systems at their core, even though haze, clouds, and aerosols can meaningfully modify those systems around the edges. Pluto's atmosphere, by contrast, turns out to be so thin, and its haze layer so unusually active and efficient at radiating heat, that the haze itself has effectively taken over as the dominant climate-controlling mechanism, a role gas typically plays essentially everywhere else scientists have studied in detail. That's precisely why researchers describe this specific climate mechanism as unique within the solar system. Nowhere else has this particular haze as thermostat dynamic been confirmed to actually dominate a world's overall temperature regulation this way. It's worth being precise about what makes this discovery credible science rather than simple speculation. It wasn't found by accident, and it wasn't discovered blind. Zhang's team specifically predicted, back in 2017, exactly the kind of infrared signature Webb should observe if the haze really was behaving this way, years before any telescope existed capable of actually testing that prediction. When Webb's 2022 observation, fully analyzed and published in 2025, matched that specific prediction, it represented a genuine, successful test of a falsifiable scientific hypothesis, not merely an unexpected surprise stumbled upon after the fact. That distinction matters enormously in how seriously the broader scientific community treats a finding like this. A specific, advanced prediction that later gets confirmed by independent observation is considerably stronger evidence than simply noticing an interesting pattern retroactively in data, collected without any prior hypothesis to test against. It's also worth being clear about what this discovery does not claim, since some less careful coverage of Pluto research has, at times, drifted into considerably more sensationalized territory. Claims of mysterious heat anomalies, suggesting hidden subsurface activity, or vague talk of unexplained bright light arrangements, framed with dramatic, alarmist language. None of that exaggerated framing reflects what the actual peer-reviewed research published by Bertrand's and Zhang's teams has reported. The real verified finding here is narrower and arguably more scientifically interesting precisely because it's specific and testable. Pluto's haze layer functions as an unusually effective standalone climate regulation mechanism, confirmed through careful thermal modeling and cross-checked against a hypothesis proposed years in advance. That's a genuinely significant scientific result on its own, without needing any embellishment to make it worth paying attention to. It's worth appreciating, too, just how unusual it is for a single dwarf planet, roughly 2/3 the diameter of Earth's own moon, orbiting more than 3 billion miles from the Sun, to demonstrate a climate mechanism this scientifically significant. Pluto's extreme distance means it receives only a tiny fraction of the sunlight Earth does, and its correspondingly thin, wispy atmosphere might reasonably have been expected to behave in a relatively simple, unremarkable way, dominated by straightforward gas physics with little room for surprises. Instead, it turns out to host one of the most distinctive, actively studied atmospheric mechanisms currently known anywhere in the solar system. A genuine reminder that even the smallest, coldest, most distant worlds humanity has managed to study up close can still overturn assumptions built up over decades of theoretical modeling. It's worth stepping back and asking why a climate quirk on a small, distant, icy world at the edge of our solar system deserves this much scientific attention. Because Pluto's haze-driven climate system offers planetary scientists a genuinely new physical mechanism to study and understand, one that may not be limited to Pluto alone. Similar high-altitude hazes have been observed on other bodies throughout the solar system and beyond, including Saturn's moon Titan, which features its own thick, complex atmospheric haze layer, and increasingly in the atmospheres of certain exoplanets studied through transit spectroscopy. Understanding precisely how Pluto's haze manages to so effectively dominate its climate, essentially overriding the influence its thin gas atmosphere would otherwise have, gives researchers a valuable, concrete, real-world test case for refining broader atmospheric models. Models that get applied not just to other icy worlds within our own solar system, but increasingly to the atmospheres of planets discovered orbiting entirely different stars, where haze and cloud layers are already known to significantly complicate efforts to characterize distant, potentially habitable worlds. Titan, in particular, offers a genuinely useful point of comparison. Saturn's largest moon is wrapped in a thick, orange-tinted haze so dense that it completely obscured its surface from view until NASA's Cassini mission and the European Space Agency's Huygens probe finally managed to see through it in the mid-2000s. Titan's haze is considerably thicker and chemically more complex than Pluto's, but both worlds share the same basic underlying puzzle. Understanding exactly how a layer of solid, suspended particles interacts with, and, in Pluto's case apparently dominates, the surrounding atmosphere's overall temperature and behavior. Lessons learned from carefully modeling Pluto's comparatively simpler, more thoroughly characterized haze system may end up directly informing how scientists interpret Titan's considerably more complex one, and vice versa. Each world's haze effectively serving as a natural laboratory for understanding the other. This finding also has real, direct implications for future exploration plans. Zhang and his colleagues have specifically noted that this kind of confirmed model-refining data helps inform what any future dedicated Pluto mission might need to specifically investigate. New Horizons, despite its historic 2015 flyby, only had a single brief pass to gather data during one specific moment in Pluto's extremely long 248-year orbital cycle around the Sun, meaning it captured only a narrow snapshot of Pluto's climate, rather than any sense of how that climate changes over Pluto's much longer seasonal cycle. Webb, by contrast, can return to observe Pluto repeatedly over time, from Earth's own orbital vantage point, and NASA researchers have specifically expressed interest in exactly that kind of follow-up. Using Webb to track Pluto across multiple observing seasons, watching for genuine seasonal variation in its haze and atmosphere, and searching for any subtler evidence of internal activity, including the long-debated, still unconfirmed possibility of a subsurface ocean lying beneath Pluto's icy crust. There's also a broader, genuinely inspiring detail worth appreciating in how this entire discovery came together. A testable prediction made in 2017, based on data from a spacecraft flyby that happened in 2015, finally confirmed in 2025 using an entirely different telescope that hadn't even launched yet when the original prediction was first proposed. That's an unusually clean, complete example of the scientific method actually playing out exactly as intended across nearly a full decade and multiple entirely separate missions, each contributing a distinct piece to the same gradually completed picture. So here's where this genuinely stands right now. In 2022, using its mid-infrared instrument, the James Webb Space Telescope achieved something no previous telescope had managed, cleanly separating Pluto's faint thermal signal from that of its large moon Charon. Fully analyzed and published across 2025, that data revealed a genuinely surprising climate mechanism. Pluto's atmosphere is regulated primarily not by its own thin nitrogen-methane gas, but by a high-altitude haze layer functioning as an unusually efficient natural thermostat, keeping the dwarf planet's upper atmosphere roughly 30 degrees Fahrenheit colder than standard gas-only models had predicted. That result specifically precisely confirmed a testable prediction Zhejiang's team had made all the way back in 2017, years before Webb even existed to check it. Webb's same 2022 observation also revealed new detail about a genuinely unique phenomenon in our solar system, material actively transferring from Pluto's thin atmosphere onto the polar regions of its companion moon Charon, an interaction found nowhere else among the planets and moons we've studied. NASA researchers are now specifically interested in returning to observe Pluto again with Webb, hoping to track how its haze and atmosphere change across a genuine seasonal cycle, and to search more carefully for any additional signs of subsurface activity that might still be hiding beneath its icy surface. The real question isn't whether Pluto still has genuine surprises left to reveal, even after New Horizons' historic 2015 flyby. This discovery already proves it clearly does. The real question is what a longer-term, repeated observing campaign with Webb might reveal about how this unusual haze-dominated climate system changes as Pluto moves through its 248-year orbit, and whether the same fundamental haze as thermostat mechanism discovered here turns out to be relevant to other hazy worlds throughout the solar system, and potentially to distant exoplanets astronomers are only just beginning to characterize in similar detail. If you want to be here for the next round of Webb's Pluto observations, or when researchers finally get closer to confirming or ruling out a subsurface ocean, subscribe to the channel and turn on notifications. Because when that research comes out, we'll break it down here, with the real data, not the invented version. One haze layer, one 8-year-old prediction, finally confirmed, a climate system unlike anything else in the solar system. Whatever future observations eventually reveal about Pluto's longer seasonal cycle, this discovery already stands as one of the clearest examples in recent planetary science of the scientific method working exactly as intended. A hypothesis proposed, a technology gap acknowledged, years of patient waiting, and finally, a precise, satisfying confirmation once the right instrument was finally pointed in the right direction. Thanks for watching.